Heyo, y'all, this is Chrissy, and I am coming at you with part 4. So, previously we were talking about thin films. So, thin films cause destructive interference when they are substantially smaller than the wavelength itself. Now, when we talk about a thin film, we're not really talking about something like plastic wrap or something. We're not actually talking about like plastic wrap. We're talking about something that has a wavelength, we're talking about something that is thinner than the wavelength of the light itself. So thinner than like 600 nanometers is the point of reference that we've been using. So that gives destructive interference from the 180 phase shift. But we can also talk about thicker films. So with a thicker film, we get a different phenomena. From a thicker film, when a film hits something with a larger index of refraction, we get a phase shift from the top. So we get 180-degree phase shift from the top. So like that, and then something like that bounces off like that. I think I drew that right with the phase shift. But, so we get that. But you can imagine that if this wavelength is being transmitted, then it could keep going through here, bounce off there, and in the end we get an extra amount of wavelength that's being added here. So this, for example, could start to come out like that. If this is what's being reflected and this is what's being reflected, you can see that in this case these two would cancel out. But if the layer is of a different thickness, it might just be that they could form constructive interference. So the reflection has to do with the thickness of the film that we're dealing with. So these are thicker materials. It has an extra path length of 2t, so 2 times the thickness of it. Because this is at an exaggerated angle here. This angle is exaggerated. You can think of it more as going like that and that, which if it travels down a distance of t and travels back up a distance of t, then you can see that that would cause a phase shift. Or it would travel 2 times the thickness of the film. To keep track of this, so we have that a phase change occurs when n increases, where n is the index of refraction. So we have 2 conditions, and they're flipped from each other. So there's the condition where we're looking for constructive interference with either 0 or 2 reflective phase changes, or destructive with 1 phase change. So you have to keep track of the number of phase changes that you're encountering. If what you are looking for falls under either of these conditions, you would use this equation to get the relevant information. So we have 2t is equal to m, the maxima, times the wavelength of the film divided by n. So that is going to give you the condition for constructive interference with 0 or 2 reflective phase changes, or destructive interference with 1 phase change. For the flip side of that, we use 2t equals m plus 1/2 lambda film over n. If this doesn't seem to have a whole lot of context to it now, we'll do an example on the next page that will show you how the questions would be asked, and that should clear it up a bit. Bear in mind that the wavelength of the film lambda film is equal to the wavelength in the vacuum divided by the index of refraction. The usefulness of this is that we can use it to measure thin layers. So we can find, let's say that we have constructive interference with 2 reflective phase changes. How thick is the film? That could be something that you're asked. So if this doesn't seem to have a whole lot of context yet, that's okay. We'll get into it on the next page. A film with index of refraction 1.6 is deposited on glass. What is the thinnest film that will produce constructive interference in the reflection of light with wavelength 550 nanometers? This is how we want to set up the picture. This is how we would want to draw it. So we've got our glass down here. That's got an index of refraction of 1.5. And then we've got our film up here. The film is much thinner than the glass. I'm going to call this a film of science goo. So the science goo has an index of refraction of 1.6. We want to find the thinnest that we can get it to have constructive interference. To do that, we're going to want to use these equations from the other page. The question is, which one do we want to use? Which one we use depends on the number of phase changes. So you use this one if you have 0 or 2 phase changes for constructive. Use this one if you have 1 phase change for constructive. Let's count the number of phase changes. As a light beam goes down, it hits the glass, or it hits the science goo. So first it hits the science goo. This has a higher index of refraction than what's up here. Usually you can infer that whatever it's starting in is air, unless it says otherwise. So we're just going to say that it's going from air into the science goo. The science goo has an index of refraction that is greater than the air. So we get a phase change. So that's 1 phase change right there. Then it's going to go down and it's going to hit the barrier between the glass and the goo. The glass has a smaller index of refraction than the goo does. So even though it reflects off, it does not have a phase change. So there's no phase change at this point. So we are still at 1 phase change. Then it's going to bounce back up and go out. At this barrier, we have a higher index here, lower index here, no phase change. So there's only 1 phase change in this setup. We only care about the science goo. We don't care about the glass. So we only count the phase changes in the film. Looking at that, we have 1 phase change and we're looking for constructive interference. That means that we are going to want to use this equation here, constructive with 1 reflective phase change. Our equation is 2t equals m plus 1/2 lambda of the lambda over n. The thinnest film is going to be at the 0th maxima. So the first constructive interference that you'll observe will be at the central maxima, so at m equals 0. So the thinnest film at m equals 0. That should always be the case. The thinnest film for constructive interference should be at m equals 0. We can now plug in. We are looking for T. T is our thickness. So T is that, not the 1.6, the thickness of the science goo. So 2T equals 0 plus 1/2 times 550 times 10 to the minus 9 meters over 1.6. And we get that the thickness, the smallest thickness of the film that we can have is 85.9 nanometers. So with these, you have to count the phase changes, realize that you're only using the phase changes in the film if we're looking for reflection, and then you have to use the correct equation. Single slit diffraction. We know that we can get diffraction from double slits. We've been working with that. But you can also get diffraction from a singular slit. It's not as recognizable, however, it's not as recognizable because the slit needs to be really small, which often doesn't let it be particularly bright. But you can have single slit diffraction. You can think of this as we have a small opening and we're going to have 4 individual waves going out of it, passing through it. Each wave is a light that spreads out, kind of like a wave on the ocean. It creates a diffraction pattern on the screen. Think of the screen as being like there. So where each of these meet and hit the screen, we get a bright spot. We also have waves that go through the center. These waves that go directly through the center all have the same path length. So they arrive in phase with each other at the screen. That's what makes the central maximum. Let's end part 4 here, and we will pick it up in part 5.